Hey guys, continuing on with graphing the sine and the cosine, we want to look a little deeper. Not every graph that we get is just going to be, give me y equals sine x, right? We may have a multiplication by some number out front, and we might even change something about x. For now, we're just going to look at what happens if we take and multiply the result by a 3 in this case. So our a up here is 3. Now, essentially what's happening here is, let's just think if it were still just y equals sine x. So our old output for sine of pi over 2 is 1, and this says take 3 times old output. So essentially what's happening here is that the y coordinate gets multiplied by 3, vertically stretched by a factor of 3. And so we can kind of see what happens with any a here. But so here's our original sine. And then after we take it and modify it to be, see, this is the original sine. And if we take it and modify it to be y equals 3 times this, what used to be just sine, notice how that it's going up much higher and dropping much lower. Okay, so so let's talk about the domain and the range of the sine. So the domain, it says you can keep going and doing this little squiggle, keep repeating this sine behavior all the way to the end of the number line and all the way to the end of and there is no end, so we call that negative infinity to infinity, all right? So that would be our domain. Now the range started out, the lowest value we ever dropped to was a -1 for our output, and the highest value, so we basically box it in, or not box it in, but we close it in these lower and upper boundaries. So the range would be from -1 is the lower boundary to +1 is the upper boundary. Okay, so domain, negative infinity to infinity, range, -1 to 1. And I'm including the endpoints for -1 and 1. Now, if we change that with the y equals a times sine of x, and our a is 3, and we're multiplying all of our y values by a factor of 3, and it drops down to its lowest point at 3 times -1 or -3, and it rises to a +3. So now our domain is still going to be from negative infinity to infinity. All right, and I know it's disappearing, but and then our range is going to go from -3 to 3 this time. Okay, so we didn't change the domain, but we did change the range when we created this new one. Okay, so multiply by 3, vertical stretch by a factor of 3. Let's look at some more situations here. Let's see. Okay, so this time we're not only going to put something out here for a, we are also going to make a modification on the inside here with this value that we'll call that omega. So in this case, omega equals 2 and a equals -2, right? There's the a on the outside, there's the omega on the inside. So gee, I wonder how that modifies the graph. So we'll have to take a look at that as well. Okay. All right, so with the sine in the original case, before we do anything, and then we've got this -2 here, right? So we're going to be multiplying by -2, or in this case, they show us that they're going to multiply it by a -1 first to cause the reflection, and then multiply it by 2. Okay, so the same result, we'd get the same result if we multiplied by -2. And then what's going on with the omega here? Okay, so we're going to show some more of those transforms. All right, so when we multiplied by the -2, what used to be 1 turned into -2 down here. Okay, and then +2 up here. So notice it not only did it increase the range, okay, we call that the amplitude. That's why that's an A. We'll learn that later. but we also flipped it over the axis because of that negative. So it used to top out right here. Then they multiplied it by -1, which took it down here. And then they multiplied it by 2, which took it to -2. So same result as multiplying by -2. Now, what happened with omega is that it's going to change any x value by a factor of a half. So essentially what we did here, omega was 2, is we took the old x value and we divided it by omega. So what used to be x now becomes x divided by omega. What used to be y now becomes a times y. Okay, we'll summarize this in another slide. Okay, so our period now, we get a full period just with a pi instead of what used to be a period of 2 pi. By this omega, we squeeze the period, it happens faster, and it only takes pi to get through the period if we're talking about this modification of the original sign. So it's a transformation is what they call that. You might have seen those in knowledge algebra, transformation of functions. So we can transform the trig functions as well. And so it'd be nice if we had just a process we could take to make this happen without having to rethink it every time. So let's look at those results. If you think about what we just described, we can look at it like this. All right, so we need omega to be greater than 0, but we know how to do that because if omega was less than 0, we can just remember that a sine of -x is equal to a negative sine of x. Remember that odd function property? And if we're looking at a cosine of -x comes back to a cosine of x. So if w is negative, we can always make it positive by using one of those two identities. Okay, so anytime we recognize this out front and this inside, we're going to take any point that was one of our, think about our 5 key points that we started our sign with. We can take each of those 5 key points and then recalculate the coordinates by taking the original x, dividing by the omega, and the original y multiplied by a. Okay, and then in that case, we've transformed the points to fit whatever function we described, cosine or sine, with some multiple on the inside and some multiple on the outside. And really, this is just a natural extension of what we discussed in the college algebra class for transformation of functions. Okay, so this next slide for example 3 asks us to take the cosine function and modify it with an a of 2 and the omega is 3. And so what we're going to do is, let's come over here. All right, so remember this is what the cosine looked like to begin with, graph of the cosine. So we're going to take these key points and use that transformation. So remember that we said any xy is going to transform to be a x divided by the omega part and a times the y part. Okay, so let's start with our 0, 1. Now, first of all, we need to know that a is 2, right? If I look at our y equals 2 cosine 3x, a is equal to 2 and omega is equal to 3. So we're going to take the point 0, 1, and we're going to create the point 0 divided by omega, which is 3, and then 2 times 1. Okay, so that means that 0, 1 becomes 0 over 3 is still 0. 2 times 1 is 2. Let's take our next point, pi over 2, 0. Okay, so I'm going to take that pi over 2. If I take pi over 2 divided by 3, okay, remember that's like 3 over 1. So the 1 flips up here times the pi, and then the 3 times 2. So that's going to turn into a pi over 6. Okay, pi over 2 divided by 3 is pi over 6. And then our old x was 0, so if I take 2 times 0, of course, I'm still going to get 0. So the second point is going to become pi over 6, 0. All right, third point began as pi, and it outputs a -1 there. So that's going to take the pi over omega, so pi over 3 is our new x, and then 2 times -1. All right, so we have 3 out of the 5 points now. It's pi over 3 and -2 for what used to be pi -1. All right, so we got that one, we got that one, we got this one. We're on this one here, so we need to take, I'm going to come down here, I'm out of room up there. So 3 pi over 2, divide that by 3. Remember, flip that up there, so the 3's are going to cancel, and we're going to end up with good old pi over 2. So 3 pi over 2, 0 is going to become pi over 2, and 2 times 0 is still 0. Okay, so we got that one. And let's get this last one. So 2 pi divided by 3 is already in lowest terms, and then I'm going to take 2 times 1, right? Okay, so for our last point, we end up with 2 pi over 3 and 2. Okay, so we got that one as well. All right, so we could graph this now if we have our coordinates so designed. What I'd like to do instead here, I just want to test our results. So remember 0, 1 changed to 0, 2. Pi over 2, 0 changed to pi over 6, 0. Pi -1 changed to pi over 3, -2. And 3 pi over 2, 0 is now pi over 2, 0. 2 pi 0, this was 2 pi 1. Sorry, I said 0. 2 pi 1 changed to 2 pi over 3, 2. Okay, so what we're really interested in are these points. So the graph's getting a little busy. I don't want to regraph it there, so let's do this instead. Okay, I've snuck my little Desmos calculator in here, graphing calculator, and I'm going to go ahead and edit in our new points. Okay, so our new point should be 0, 2. And in Desmos, you can separate coordinates with a comma in one line. So I'm going to put the pi over 6. And 0. And we got pi over 3, -2. Pi over 2, 0. And finally, 2 pi over 3, 2. Okay, kind of scrolled off the screen there. Let me bring these back in there. Okay, so there's our new 5 key points. Notice how they're kind of squeezed together. So I'm now going to create the graph of our modified function. So y is equal to 2 cosine of 3x. Okay, and you can see that all the points we recalculated fall on this new graph. And we started with the points from the simple graph of cosine. Okay, so that function right there, notice how what we did is we squeezed the period into a shorter amount. Okay, and here we are back at that original question. So let's see how the text is following through on this. So if we look at, they do the stretch vertically by a factor of 2. So that makes our range go from -2 to 2 at this point. Okay, so that's this part here, the A, the amplitude. And then multiplying by a factor of 1/3. So we divided by 3, that's the same thing. And that's changing the length of a period. So now if we look at this result, it's still the domain goes from -infinity to infinity. That won't change. But the range is now between -2 and 2. And if we look at the way we saw this on the Desmos graph, this was the original cosine. And when we squeezed it by that factor of 1/3, we made the period shorter. So what used to be a period of 2 pi is now a period of 2 pi over 3. Notice that the x coordinate goes from 0, and then the next top is at 2 pi over 3 here. Okay. And in fact, if we think about, if we were to shift the graph of the cosine so that it's just the simple sine and cosine, if we shifted the graphs by a distance of pi over 2, either left or right, they would actually land on top of each other. So they're both sinusoidal graphs, kind of hard to say. And there's a lot of applications. For example, sound waves have that kind of motion, and lots of other applications in physics. Okay, and that brings us to this theorem here. And the theorem says that we want to start with omega greater than 0, but we can always make that happen with the even or odd properties. And if we have a number in front and then a number multiplier on the inside here, we're going to take the absolute value. Remember, that could be negative. So you still want to multiply by the negative when you're changing your y coordinate. But if you're calculating the amplitude, just give the absolute value. That tells you how high and how low the graph goes. And then the period, we're going to start to refer to that as t. So we had a period that started out as 2 pi. And our new period, after we transformed that cosine, turned out to be 2 pi over 3, because our omega was 3. And so that's a general rule. If I have a period to begin with that's 2 pi, then my new period is going to be calculated by taking my old period 2 pi and dividing by the omega piece. So we'll call that period t from now on. Yeah, that brings us to a pretty straightforward question here. It wants to know what's the amplitude and period of y equals 5 times the sine of 3x. Okay, so remember, for the amplitude, we're going to take the absolute value of a is equal to 5, right? And omega is 3. So the amplitude, remember the amplitude, the absolute value of A is already positive, so it's not going to change. But we take the absolute value of 5, so that's the amplitude. Okay, A is not necessarily the amplitude, but we need it to get the amplitude. The amplitude is the absolute value of A. Had this been a -5, 5 would still be the amplitude, but the transformation would be different. Omega is equal to 3, so we know that the original period was 2 pi, so period is equal to 2 pi over 3. And there it is. Okay, so we've seen this slide before. I just want to add that new power to it. This helps us transform points, but we also want to say that the amplitude is that, period is 2 pi over omega. Okay, so let's exercise this one more time with the graph of a sine. Works for both a sine and a cosine, and they both start out with a 2 pi period. If we're talking about the sine, the key 5 points start out as 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi 0. And we can find a is 2 and omega is 2. So let's use that to find the corresponding transform points. Okay, so we should probably do it on this slide. The new x coordinates are going to be x over omega, so that's going to be a 0 over 2, a pi over 4, a pi over 2, and 3 pi over 4, and pi, right? If I divide each of these by 2. Then the y coordinates are all going to be multiplied by 2, so that's going to be 2 times 0 is 0, 2 times 1 is 2, 2 times 0 is 0, 2 times negative 1 is negative 2, and then 2 times 0 is 0 again. Okay, and we know that the period is going to be 2 pi over 2, right? Original period over omega, omega was 2, so that's our new period of just pi. And we called our period t, right? So pi is the period. Absolute value of 2, or 2 is the amplitude. Okay, and here's the graph of just the 5 points that we found recalculated. If we realize that our period happens in pi, then we can extend that and just take this little picture and copy it, paste it right back here, and go each direction. And then we would just put this little arrow saying, okay, what we're doing here goes on forever. By the way, any point that you land at that you've recalculated, you can find its corresponding point in the next period by adding the period to it. So it's going to happen at a distance of pi. So if I add another pi to pi over 2, I should be at a 0 again. If I add another pi to 3 pi over 4, I'm down at my negative 2 again. One last thing to mention here is that since our period is now pi, and I've got 5 key points in my period, or one cycle, then I can divide the period by 4 to split that period into the 4 sections made up by the 5 points. So it takes those 5 points to make 4 sections, and each of those key points are now, we can place each of those pi over 4 radians between one another. So to get to the next key point from, say, this origin, I have to go pi over 4. To get to the next key point, I add another pi over 4, so that makes a pi over 2. Add the next pi over 4, I got 3 pi over 4, 4 pi over 4, I'm at pi. Add another pi over 4, my next key point. So 4 pi over 4s make up a total period pi, right? 4 times that. So we can just split it into 4s and know where each of our key points are going to land in either direction. Add it to go right, subtract it to go left.